Okay, in this second lecture, but actually lecture 1, we're going to talk about basic definitions. So this might be the most boring parts of this course because we're going to cover or review all the definitions that we need. So first of all, let me start with the graphs. So what is a graph? Right. So typically, we want to represent graph as a set of pairs of a vertex set and edge set. So let me first remind you the definitions that you may have seen. So the V is a finite set and E is a set of subsets of size 2 of V. So if this is our definitions, then let me give an example. So this, let's say this is 1, 2, 3, 4, and this is represented by a pair of finite set 1, 2, 3, 4, and you have edges like 1, 4, 1, 2, and 2, 3. And this might be a perfect definitions if you want to study the simple graphs. But unfortunately, this cannot cover all cases, all possible things. For instance, I mean, how can I have a loop? So what is a loop? Loop is an edge which is instant with only one vertex. So, okay, then we may modify definitions as follows. So V is a finite set and E is set of subsets of size 1 or 2 of V, right? So in that case, for instance, you might have a 1, 2, 3, 4, and the edge set could be like 1, 4, and 2, 1, and 2. So what is this? This means that you have 4 vertices, 1, 2, 3, 4, and 1 and 4 are adjacent. There's an edge. So this is an edge. Oops, yeah. And 2, 1 are adjacent, but 2 is not adjacent to set because this is that. So that's a loop. So this this definition allows you to describe a little bit more because now you can express loops. But still, you may wish to have a parallel edges. And this definition doesn't allow you to represent parallel edges. What are the parallel edges? 2 edges are parallel if it looks like this, where they have the same set of ends. So, in order to have parallel edges, sometimes some authors use multi-sets instead of set, right? So instead of saying E is a set of subsets of size 1 or 2, you may want to say E is a multi-set of subsets of size 1 or 2. By saying so, we allow same member to be in a set, multi-set, maybe twice or 3 times more. But there's another way of defining a graph more precisely. So, okay, the reason why I'm saying all these definitions, different definitions of graphs, is because depending on the context, people use different definitions for graphs. So whenever people write write a paper on the graphs, sometimes we use one definition, sometimes we use the other definitions. Even for me, I would say if this paper doesn't use any loops or parallel edges, then I would stick to the simple definition where you don't allow loops and parallel edges. If I use a lot of parallel edges and loops, I would use other definitions that I'm going to describe. All right, so here's a real definition of graph for this course. Okay. Yeah. Okay, let me go to the next page. So what is graph? A graph is an ordered pair. Okay, we don't have to say ordered. A pair V E of a finite set V. So V is a finite set and a finite set E. And now I don't care. I don't say that E is a set of subsets of V. E could be anything. So you can think of E as a set of labels of edges. V is a set of labels of vertices. And there's an implicit incidence relation with an incidence relation. Okay, let's say graph G. Okay, so incidence relation between V and E. And there are so many ways to make a wrong definition, so I have to be careful. Such that, now what should we say? So instance relation says that a vertex is instant with an edge. Okay. So when is this vertex instant with edge? That's so if we so this is what the instance relation describes. So in order to say this is a graph, so that each E in E is so incident with one or two vertices. Well, the vertices. What is vertices? Elements of V. Right? So every edge is instant with one or two vertices. That's the condition. If you want to be super precise, we may have to write graph as a triple set of vertices, set of edges, and these instance relations. But indeed, this last one is hidden because we don't really write it down. So normally we just say graph is a pair of vertex set and edge set, but there's some hidden relations between vertices and edges satisfying certain conditions. All right, so let me define a few more terms. Okay, so for instance, I have to give you an example. So if this is 1, 2, 3, 4, and I have parallel edges and loops. Now the edges have names A, B, C, D, E, and then what is the graph? V is 1, 2, 3, 4, and E is A, B, C, D, E, and what is the instance relation? So 1, okay. So this is actually a subset of V times E, right? So it could be 1A and 2A, yes, and 1B, 3B, and 1C, 3C, and 3D, 4D, and 4E, right? So this instance relation is actually a set of pairs of a vertex, and an edge. So I didn't say what a vertex is. So an element of V is called a vertex of G. An element of E is called an edge of G. And what else? We write V of G to denote the vertex set, E of G to denote the edge set. Set of edges of G, this is set of vertices of G. All right, what else? And if E is instant, okay, the set of vertices incident with E is called the set of ends of E. So if I have an edge A which is instant with 2, 1, 2, then 1, 2 are the ends of E in this case, right? All right. So an edge is a loop if it has only one end, right? Every edge has one or two ends, and if you have only one end, then that's a loop. All right. Two vertices VW are adjacent. Okay, adjacent if there is an edge E whose set of ends is VW, right? If you have an edge instant with both V and W, then we say that two vertices V is adjacent to W, right? So or V is adjacent to W. And then we also say that V is a neighbor of W. Okay. And two edges are parallel if they have the same set of ends. Okay, so if you have two edges which are A, B, 1, 2, they both share the 1, 2 as the set of ends. In this case, we say that these one A, B are parallel. Now, so we have defined the instance relations. So A is instant with 1, 1 is instant with A, and we define the adjacency relations. 1 is adjacent to 2, and we say what a loop is, what the vertex, what the parallel edges are, and neighbors. So we define most of the terminologies for describing graphs. And this is what we're going to use for this whole course. So And even though we use Reinhard Dister's book as our main reference book, we have different terminologies, so that's what we have to be careful. So in his book, graph in his book doesn't have parallel edges. For us, we're gonna have parallel edges. We allow parallel edges and loops, so that's different. So when you read a book or paper on graph theory, you have to be careful what graphs this paper or textbook is talking about. And whenever I write a paper, maybe in the first part or in the beginning of section 2, usually I say that in this paper we assume graphs have no loops, or we assume graph may have our graphs may have loops or parallel edges. We always try to say what a graph is. Okay, so I forgot to say one last thing. A graph is simple if it has no loops, no parallel edges. So some authors, depending on the terminologies, so we are going to use this term, simple graphs and graphs. And sometimes, people use graphs for simple graphs and the multigraphs for graphs. So whenever you read somebody saying multigraph, that just means a graph for us. Whenever somebody says graphs, then we have to be careful whether it's a graphs or simple graphs. In particular, this is from Dister's book. All right. Now, these are the common definitions. And now, when you have two graphs that looks like this, and let's say 11, 13, 1, minus 1, and x, y, z, technically, these two graphs are different, right? Set of vertices are not equal, set of edges are not equal. But we still want to say that these two graphs are same thing, right? Because essentially, what matters is the relations, not about the labels. So because of that, we define this isomorphism, okay? So two graphs, G and, let me say for two graphs G and H, G is isomorphic to H if there is an isomorphism, okay? If there is a mapping, okay, let me say that's phi called an isomorphism, that maps V of G to V of H and right, vertices to vertices, edges to edges, while preserving the instance relation. Okay, then we say that two graphs are isomorphic. So these two graphs are isomorphic. So graph theory is, you can say the graph theory as a study of graphs, study of the property of graphs, invariant undertaking isomorphisms, right? So we don't care about labels, but what we care is the relations. All right, so these are the definitions. So next thing we wanna do is the constructions. So let me start with the simple examples. Okay, so what are the complete graphs? Kn. This is called the complete graphs on n vertices. Okay, it's a simple graph on n vertices such that every pair of distinct vertices is adjacent to each other. So K1 is simple one vertex graph, K2 is two vertices adjacent, K3 is triangle, K4 is four vertices, K5 is five vertices, and 10 edges, 5 choose 2. That's complete graphs. And KST, okay, this is also called the complete bipartite graphs. So you have a S vertices and T vertices, and between them it's complete. There are no other edges. So for instance, K33, okay, let me say K34, you have 3 vertices and 4 vertices, and edges are like this. And it's a simple graph. So it's a simple graph on S plus T vertices, whose vertex set is partitioned into 2. Into 2 sets, A and B, with A in S, B in T, such that the set of edges is equal to, no, let me not say that, with such that no two vertices in A are adjacent, no two vertices in B are adjacent, and every vertex in A is adjacent to all vertices in B. That's a definition of KST. Alright, so it's complete bipartite graphs. Ooh, yep. And there's something called the line graphs. So let me say LG. This is not an advertisement, okay, but anyway, LG, L of G. So for graph G, the line graph of G is, okay, VE is a simple graph on E. Okay, so the vertex set of line graph of G is the edge set of G, and it's a simple graph, so I don't need to describe the instance relation. I only need to describe the adjacency relation. I only need to say which vertex is adjacent to which vertex. But the vertex of E, the vertex of the line graph is the edges of the G. So E in E is adjacent to F in E if and okay, let me say in L of G, if and only if E, F are adjacent or as edges in G. Okay, so I forgot to say the adjacency is in the graph between edges. Two edges E, F are adjacent in G if they have at least one vertex as a common end, right? So if you have a common end, then we say that these two vertices are, these two edges are adjacent. So let me give you an example. So what could be the interesting example? So I tried that. So this is 6 vertex graph. And what is line graph? So let me put numbers 1, 2, 3, 4, 5. Then in the line graph I have 5 vertices. 1, 2, 3, 4, 5. And one is adjacent to 2, one is adjacent to 3, and 2 is adjacent to 3, and 3, 4, 5. Should I try with loops and parallel edges? Okay, so 6, 7. So 6, let me put 6 here and 7 here. Oh no, I didn't create a loop. Let me create a loop. 7. Okay, so what's gonna happen? 7 is adjacent to 3, 4, 5. So let me put 7 here. And 6 is adjacent to 4 and 7. So 6 is here. So that's the line graph. So even if the graph is not simple, the line graph could be, line graph is always simple. So this is on construction. What are the other things? Okay. Well, G. Okay, maybe I say simple thing. G is an empty graph if set of edges is empty. All right, what about G is a null graph if set of vertices is empty? Well, we rarely see this null graph, so you don't have to worry. I'm just saying that because there were people who write statements on graphs, and sometimes these statements are forced on really simple cases like 0 vertex graph or 1 vertex graph. So we always want to be careful. But typically we assume that the vertex set is not empty because we don't really care. But still we want to make sure that statement is true for 1 vertex graph. That's where a lot of textbook also has mistakes. There's operations to construct a new graph from a graph. So line graph is one operation. There's something called complement of a simple graph. So we write G complement. This is a simple graph on the same vertex set such that 2 vertices x for all distinct xy in VG, x is adjacent to y in G if and only if X is non-adjacent to y in G complement. All right, so that's the complement or complement graph. So these are the common constructions and operations. Now, what's next? So next topic is the containment relations. Right, when we have a set, we talk about subsets. When we have graphs, we talk about subgraphs. Right, so here you have operations to delete an edge and delete a vertex. I already mentioned some of them in the previous lecture. Right, so for a graph G and an edge E of G delete E is a graph on the same vertex set, but set of edges is simply obtained by deleting E. And you have the same with the same instance relations induced on V times EG minus E. So that's the deletion operations. How about contractions? No, I mean, let's not do the contraction now. I will do it later. What about deleting a vertex? Graph obtained from G by deleting V, the vertex V. So V, deleting V, and when you delete a vertex, you have to delete all edges instant with V. So these are two operations. And then we say a graph H is a subgraph of G if H is obtained from G by deleting vertices and edges. That's a subgraph, and a graph H is an. Now there are two variations, I mean more stronger concept of subgraph. So what is spanning subgraph? A subgraph is spanning if H is obtained from G by deleting edges. So you didn't delete vertices, so the set of vertices is same, right? So in this case you have the same set of vertices, and a graph H is an induced subgraph of G if now instead of deleting edges we delete vertices. H is obtained from G by deleting vertices. So I cannot say that E of H is equal to E of G. I cannot say in general because when you delete a vertex, you can delete all the edges instantly with this vertex. But if you fix one set which you're not going to delete, then the induced subgraph on this set is just fixed. It's one graph. So there's a notation for that. So G bracket X is graph obtained by deleting all vertices outside of X. So this is actually induced subgraph. Induced subgraph. So we normally say subgraph. Okay, so X is a subset of vertices. So subgraph induced on X. All right. So that's subgraph. And what else? Sorry. The next thing is a subgraph. Yeah, a subgraph H is a proper subgraph of G if H is not equal to G. Right? So G itself is a subgraph of G. But when we say a proper subgraph, we exclude G. So we want to have a strictly smaller subgraph, then it's a proper subgraph. Now here's one important terminologies: minimal and maximal. And you have to be careful distinguishing minimum and maximum. So what's the difference? Right. So when we say in a collection of sets, we say that some property holds. In this set has some property, and it's minimal with respect to that property. What does that mean? That means this set satisfies this property, but it's minimal so no proper subset satisfies this property. Then we say it's a minimal set satisfying this property. When you say something is a minimum set satisfying this property, some set is minimum satisfying this property, that means it's a set satisfying this property and its size is minimum. Right? So for instance, let me say 1, 2, 1 and empty and 2. So this is so-called the Hasse diagram. Let me say I have a, okay, so 1, 2, 3 and 2, 3 and 1, 3, 1, 3. So 1, 3. Let me color some sets. Okay, it's not a good example. All right, yeah, okay, that's fine. So in this collection of sets, I can say that okay, let me use a different strategy, different coloring. So oops, yeah, 1, 2, 3, 1, 2, 1, 3, 2, 3. All right. So what I can say is, so 1, 2 is a minimal red set, right? So when I circle the set by red color, then I say it's a red set. So in this drawing, 1, 2 is a minimal red set because 1, 2 is red and no proper subset is red. And 3 is a minimal red set, right? Because 3 is red, empty set is not red. And 2, 3 is not a minimal red set. Because 2, 3 is red, but 3 is not red. However, 1, 2 is not a minimum red set because size of 1, 2 is bigger than size of 3. Okay, you have a smaller subset which still satisfies this property of being red. 3 is a minimum red set. Okay, so this is distinction between minimal and minimum. We're going to use this terminology quite often, so you have to be careful. When you say minimum, we're talking about the size. When you say minimal, we're talking about the inclusions, inclusion-wise minimal. And same thing is true for maximum and maximal. So if we say some property holds, some set is maximum, that means its size is maximum. When we say some maximal, that means no proper superset satisfies this property. And we say same thing for the graphs, right? So for instance, yeah, but we didn't say anything about graphs. Okay, yeah, so right? Let me just say a graph G is minimal let me just say this way, minimal with respect to some property with respect to some property P if G satisfies P but no proper subgraph of G satisfies P. So here instead of subset we are talking about subgraph. And this, when you say minimum, it's not the case. Minimum, then G's. When you normally you may talk about the number of edges or number of vertices, right? Depending on the context, right? So this, you might have a graph, smallest possible graphs satisfying certain property. Then we say minimum. All right, so that's the containment relation, so subgraphs. Now the next one is degrees and the paths, cycles, and connectedness. Right. So what is the degree? The degree of a vertex V of G is the number of edges incident with V. But there's one restriction. that loops are counted twice. So what does that mean? That means if I have a vertex like this, so this is 1, 2, 3, 4, and there are 4 1 A, B, C, D, E, then degree of this vertex, so we write D, E, G free. Degree of this vertex 1 is equal to you may say 5. No, actually 7. Why? Because it's 3 plus 2 times 2. Yeah, 2 is the number of loops, and each loops are counted twice. So it's a ridiculous in a sense, right? Because you may think that, oh, come on, this is number of edges, and why is the degree bigger than the number of edges of the whole graph? Why should we make it this way? The reason is to make this theorem hold. So let me show you this well-known theorem or lemma. Okay, let me say lemma. Right, so if G is a graph, then sum of the degree is equal to twice number of edges. So this is what's called the handshaking lemma. Right? Because if you have many people at the party and some pairs of people did some handshaking, some pairs didn't, and then later after the party, each people think of the number of times they did shake hands with someone else, and from that information you can get total number of times where people shake hands, right? So why is this true? This is easy lemma. You just count. So this is double counting, right? You double count the instance relations, the vertex and edge, where vertex V is instant with E. Sometimes we omit this subscript G, right? I could have written G, but let's omit it because we only have a one graph, so there's no confusion. Right, so how do we count this pair of vertex and an edge, which are instant? Well, if you count according to the vertices, then this is like for each vertex free, number of edges, instant with free. Okay, instead of that, let me just say we count the edges so that V is instant with E, or we count for every edge, we count number of vertices where V is instant with E. So we are counting same object in two different ways, so these two should be equal. Now, on the left hand side, this is nothing but the right? I mean, it's it's number of edges, right? So, well, isn't it the degree? And on the right hand side, isn't it the 2 times number of edges, because every edge has 2 ends? Well, mostly it's true, but except the case when you have a loop, then it's different, because if you look at the right hand side, this number is 1 if E is a loop. If it's 2 if E is a non-loop, right? So if you use same proof, double counting proof for this case, And if we assume that if graph has no loops, then this proof works, right? They are equal, so the sum of degree is equal to twice number of edges. Now, how can you make this to be true for general graphs? All right, if you make loops counted only once, then this equality doesn't hold. So what you do is to modify the definition of the degree, so that degree now counts 2 for loops. Then each of loop edges, this number is counted twice. So we have to modify this, right? For whenever E is a loop, then you have 2 sets of this type. All right. Then on the left-hand side, the contribution of this thing is actually the degree, right? So that's how we that's how we why we define the degree like this. Loops are counted twice. Okay, so that's the degree. Now here's the first theorem that we may see in this class, right? If G is a graph with average degree K, then G has a subgraph whose maximum degree is at least K over 2. So what does this mean? Yeah, so what is average degree? Average degree is simply just degree divided by number of vertices. The maximum degree is just the maximum degree. All right. So how do we prove this theorem? So here we're going to use the maximality. All right. So let's pick a subgraph with the maximum average degree. Subgraph H with the maximum E of H divided by let's say 2, because average degree is equal to okay, I have to be careful because but anyway, it's equal, right? I mean, sum of degree is twice number of edges. So since graph G is a graph whose average degree is K, so the H subgraph has the property that the average degree is at least K, because it's a maximum, right? And such a thing exists because given H, you only have finitely many subgraph of isomorphisms. So among all subgraphs, you can choose the one with the maximum something. There exists such a thing because you only have finitely many subgraphs of isomorphism. So there are only finitely many different values. One of them is maximum. And this property doesn't hold in the real sets, right? You cannot say that you can choose maximum real in some set of reals, because, for instance, if you have a past negative reals, set of negative reals, and the maximum real in the set doesn't exist. But in this case, we are only dealing with finitely many graphs, so you can find the subgraph H with the maximum average degree. Now, because of these assumptions, for every vertex V, when you delete V, then average degree should decrease. Oops. Let me see. Why? Because if it increases, then we're going to choose. Okay. If it increases, you will choose H delivery instead of H. Now, what does that mean? That means, okay, now I just need the calculations, right? So this is less than, right? Yes, right. So you have a V here, and now how many edges do I lose? Yeah. Okay. Should I say something about the loops? Okay. Let me not worry about loops first time, and then later see what happens. So let's say you have n vertices and you have n minus 1, right? If h is n vertices, you have n minus 1 here, and e of h minus 3, and e of h. So the e of h minus, oops, 3 is less than or equal to n minus 1 e of h. Right? So what do we get? Now, okay, let me just write n minus 1 here and n here. Okay. And should I subtract? So n times e of h minus e of h minus 3 is greater than, no. Yes, we move to the right hand side. So it's greater than e of h. So this is the left hand side. You have a number of edges decreasing. Is greater than number of edges. I mean 1 over n. All right. So what does that mean? So number of edges decreasing is greater than number of edges divided by n, which is number of edges divided by number of vertices. And I know that this number is at least k over 2. Right? So that means 3 is instant with at least k over 2 edges. And loops are counted twice, but I didn't say yet. So degree of V is at least this number. Degree of V in H is at least this number. It's not equal because you may have loops, but this is at least k over 2. Okay, so that's the proof. So if you look at this proof, what you may notice that I didn't say how to find such a graph algorithmically, right? We just start with the assumption that, okay, among all possible subgraphs, let's choose the one with maximum this number, and then magically this graph satisfies the property that you are looking for. And this is common in many proofs in graph theory. And many of these proofs can be turned into an algorithms. But actually, instead of maximum, if I say maximum, then you may want to say, oh well, I mean, if you convert this into algorithm one by one, then well, how do you go over all possible subgraphs and choose the one with the maximum something? That takes too much time, right? Because you might have exponentially many subgraphs to find it. But actually, if you understand the proof, whenever you find a vertex whose deletion decreases increases average degree, then you go for that subgraphs. So in a sense, you want to choose you start with a graph G and you delete a vertex which increases average degree. So you keep deleting a vertex. Whenever it increases average degree, at some point you will be stuck. And then that's when the maximum degrees and least k over 2. This can be implemented efficiently, right? It's the polynomial time algorithm. So even though, but the beauty of the proof, I didn't write it down in efficient way, but this still gives you the efficient algorithm. All right, so yeah, so that's it. Maybe I should change the title of this section because I may have to continue in the next video. So far in this video, we talked about the definition of graphs and constructions of some subgraphs, and then we talked about construction of some graphs, and then we talked about subgraphs, and then we have degrees, and we proved the one theorem on the degree. Okay, let's continue in the next video. Okay.